Welcome everybody to another edition of the Boulder and Denver combined Java users group, which we're doing virtually because of COVID restrictions. So first of all, thanks for joining us. If you have any ideas for upcoming talks, let us know, and we're happy to try to book whoever it is. It's great because we're doing this worldwide. We can get anybody anywhere. And we're not just restricted to Colorado. We don't have any travel restrictions with virtual broadcasts. So I'm going to go through the announcements. I'm Ostrovich. We're always looking for speakers. Let us know. Housekeeping. If you need the restroom, hopefully you can find one where you're watching the broadcast. Tech Systems. They're one of our sponsors. They've been great. They usually sponsor food, but as has been the case for every day during COVID, your dinner tonight is sponsored by whatever's in your fridge or your pantry. Courtney Elterman is our contact there. So if you have any hiring needs, please reach out to our sponsors. They help us do door prizes, and we really appreciate their support. JFrog is another sponsor, and we've been doing giveaways, and they usually have a QR code. And I'm going to bring up, or actually Matt's going to bring up Ari Waller to say a few words about some stuff that they've got going on. So, Ari, are you there? There you go.
I am. Awesome. Hi, everybody. I'm Ari Waller, the Meetup Event Manager for JFrog, and we're really excited to be a sponsor for the Denver Jug. I'll share just a little bit about who we are. JFrog is the DevOps software company. We were founded in 2008, and many people in the DevOps community know us best by our flagship product, Artifactory, written in Java, and is considered by many to be the gold standard for managing your artifacts and dependencies. But what you may not know is that JFrog actually has a free cloud version of its software available for you to use, especially for the Java Meetup community. And if you're working with Docker, as I know many of you are, JFrog's free tier on the cloud is capable of functioning as a pull-through cache for Docker Hub. And the best part is, since JFrog has partnered with Docker, you'll be exempt from the rate limits on pulls from free or anonymous accounts. We do have some great things coming up. You may recognize some of these faces. Our annual DevOps Global Conference, Swamp Up 2021, is coming May 25th to the 27th in the Americas. And JFrog wants you to get in for free. Besides this sample of some amazing Java-oriented speakers, we also have an amazing executive panel with the CEOs from HashiCorp, PagerDuty, Datadog, Elastic, and of course, JFrog. Here's where you can scan some QR codes that Greg had mentioned, and I'll drop them in the chat afterwards for the free conference day. And also, there is a free technical deep dive tutorial day add-on ticket, which is normally $49, but for those for the Denver and Boulder Jugs, that will be your entry for free on that third day. So we'll drop the links in the chat shortly. And also another bonus for tonight, and just for attendees tonight, is going to be a chance to win one of 3 Amazon Echo Dots. You can enter again with the QR code or the bit.ly link that you'll see. And 3 winners will be selected within 3 to 5 business days. And then we will share the winners on the Meetup page and, of course, in social media. So we're really excited about that. Greg, thanks again. And we're looking forward to the talk for tonight.
Awesome. Thank you, Ari. Another sponsor we have that we want to give a shout out to is Apex Systems. They usually sponsor the beer. Tonight, their beer or wine or alcohol that you have is sponsored by whatever's in your fridge. I'm actually drinking Palisade Peach by Breckenridge Brewery, which is actually kind of nice. So there you go. Thank you. And if you have any staffing needs, it's another company we want you to reach out to because we appreciate their support. And on the deck, it looks like they're hiring for Java and Spring Boot, C# and Angular, Python, and some data engineering roles. So thank you, Apex, for being a sponsor. Another sponsor is Develop Intelligence. They give away a plural site training. So if you enter in the door prizes, you could win that. And it's kind of nice. We use it at the state. We're doing a prototype of it. And Pluralsight's kind of amazing. I didn't realize how great it was. Develop Intelligence is always looking to hire. both technical instructors who specialize in several technologies for contract opportunities, as well as, I'm sure, instructors just to teach the technology. So those technologies include Java, Golang, JavaScript, React, DevOps, and tools like Kubernetes and Docker, and many others. So reach out to Bob Clary, and there's a link for him on the deck, bob at developintelligence.com. So awesome. Thank you, Develop Intelligence, for being a sponsor. Amazon is another sponsor. Chris Almond or Sam Ayer were our contacts. They're hiring for all sorts of stacks at all sorts of levels. So just reach out to them if you are looking for a gig. And we appreciate their support. We give away really cool stuff with them. Another sponsor is Okta, and we'll see if Matt pops in, but thank you. We really appreciate your support. Matt runs the meeting. Hi, Matt. Thank you. We really appreciate him doing the meeting every time for the online meeting. When we met in person, they also paid for some drinks and for some other stuff and some food. After the meeting, we would do another meeting. Obviously, that's on hold. NextGen is another sponsor. Beth Crowley and Sandy Holskin. And I guess another contact, Dana Estlund. I sort of forgot about that. Sorry, Dana. And they're really great. They're also a staffing agency. So if you're hiring, they're looking for full stack, mid to senior level Java. And this talks a little bit about that. Please reach out to them to show our appreciation for them sponsoring the Java Users Group. And we have a giveaway from them in the door prizes part of the meeting. Another sponsor is Agile Learner, Venkat's Romanian. They're awesome. They were going to have a big conference that's on hold because of COVID. I'm sure they're going to reschedule. They have training as well, and I think maybe some videos on Agile. So check them out. There's a link to the website, agilelearner.com, and we appreciate their support of your Denver Java Users Group and your Boulder Java Users Group. Another sponsor is JetBrains. They give away a free IDE. They've been doing it for over a decade, and we really appreciate their support. Over a decade. And so thank you to that, and we give away a couple of them, and it's an awesome deal. We have a link for the door prizes. It should be in the chat for the stream. And you're just going to click that link, and it's a form to fill out if you want to be entered in with the door prizes. And there it is. It's showing up on my screen. So thank you for all the sponsors that give away cool stuff that we give to you. Another thank you to the DJUG board, Matt Rabel, who does the speakers, locations, handles the broadcast. We really appreciate that, Matt. Mike Zuedo, who handles all the stuff with the door prizes and is acting as a backup role if he needs to for the broadcast. And Zeddy Chinfang, who does all sorts of great operational stuff, including social media, announcements, etc. So now I'm going to bring up Chris Woina, who's from the Boulder Java Users Group, and he'd like to thank a few people as well.
Thanks, Greg. Of course, many of the same people, Tech Systems. We work with James Corboy. They're a great resource, even just to talk to about finding out what's going on. Rule for Cybersecurity and Emerging Technologies. They were the 2019 Colorado Technology Association Award winner, and I think last year's CEO of Colorado winner. No Fluff, Just Stuff, Jay Zimmerman, world-class conferences and training. They have one coming up at the end of the month. They'll be doing virtually. Agile developer, Venkat Subramanian. If anybody's interested in getting a comp to their training, the first person that contacts me, I'll get that to you. JetBrains IntelliJ, and also O'Reilly Books. Thanks, Greg.
Thank you. Thank you, Chris. So tonight's presentation is managing state in Elastic Microservices. Scaling stateless services is easy, but scaling their stateful data stores, not so much. This is true whether you're using an old-fashioned relational database or one of the popular modern KV data stores, such as MongoDB or Redis. In this presentation, we're going to hear about some of the issues with state management in Elastic Microservices today, and look into how Coherence Community Edition, with its Helidon and Eclipse MicroProfile integration, provides a better alternative that you can start using tomorrow. For tonight's speaker, Aleks Seović is an architect at Oracle, where he works on Oracle Coherence, a leading in-memory data grid product, and contributes to the Helidon microservices framework. Most recently, Aleks led the design and implementation of the Helidon gRPC framework, as well as CDI and Eclipse MicroProfile support in Coherence. He currently leads the implementation of Coherence native clients, GraphQL support, and Spring integration. Prior to joining Oracle in 2016, Aleks led a boutique consultancy practice where he worked with customers around the world to help them implement mission-critical applications on top of Coherence. Aleks is the author of Oracle Coherence 3.5, and it's put out by Pact Publishing, and that came out in 2010. And he frequently speaks about and evangelizes Coherence at industry conferences, Java and .NET user group events, and Coherence special interest groups. So without further ado, thank you for coming tonight, and let me bring up Aleks Seović.
Thank you, Greg. Thanks for the introduction. So you kind of took my first minute of telling everybody what the talk is about by actually doing it for me.
You can have an extra minute, but remember, no more than 4 hours. You've got to cut it before that.
Yep. So without further ado, I think you heard who I am, what I do, and what the presentation is about. So let's get started and talk about what the issues with state management in microservices are and how can Coherence help you. So we're going to be using a demo application that I actually found when I was starting to work on this and try to figure out how I would build some microservice application with Coherence. I found this, which was supposed to be like canonical microservices demo, kind of like what according to their documentation, basically what PetStore did for Java EE. This was the attempt to do it for microservices. Now, it never became as well known as the PetStore was back in the day, but still, it's a pretty decent example, and this is where you can find the original microservices-demo GitHub.io. So the application itself is basically an e-commerce site, which has a number of services that are deployed as separate, that are implemented and deployed as separate microservices. So starting from a front end, we have typical services you would expect to find in the e-commerce websites, such as catalog that you can store the products and browse the products in, user management service, order service, shopping cart service, and then there is also payment and shipping service, which order service itself uses to process orders. So the original SockShop implementation uses number of technologies. I guess one of the things that they wanted to show was that you can use, you can build microservices in a polyglot fashion. So you can use different languages. You can use different, you can also have polyglot persistence as well. So you can use different data stores, et cetera, et cetera. So they did front end using Node.js and Express. They have several Spring Boot services that are written in Java, such as shopping cart and order service and shipping service. And two of those use MongoDB as a backend data store. They also have some Go services that are built using some Go framework. I'm not really familiar. GoKit, I think, is called. So, and then those again, one uses MongoDB and one uses MySQL. So that's really the original. The architecture of the original implementation. And I will switch and just show you what the final product looks like. So this is how the application looks like, and I will probably have to log in again because I logged out, but once I log in, I can browse the product catalog. Okay. So I can browse the product catalog. I can add products to shopping cart, and then I can go see what's in a shopping cart, update quantity, etc. Stuff that you can typically do when you're buying stuff online. And then proceed to checkout, and then I can see that my order has been placed. It's this one, and you can see what's in the order. So that's really from a functional perspective, what the application does. I'm sorry. So what's wrong with it? I mean, really nothing. I mean, this is how we build application for a while now. This is, architecture is something that most of us are fairly familiar with, right? But there are some downsides to it, right? I mean, for one, are these services truly scalable, right? And by that, I mean, can you scale both the data persistence layer, whether it's your Mongo or MySQL or whatever, as well as your stateless REST application, right? Or front end or whatever, right? Second thing is, are they highly available? What happens, obviously, if we have something that can be scaled out and is stateless, it is highly available because you can always, if one of them dies, we still have a bunch of them left to handle the incoming request. But what happens if your data store is down? If your data store is not scalable, then if your data store goes down, your whole application is effectively down. And then the last but not least, these things tend to, as they grow, and especially as they scale and are built to handle significant load, and once you scale them out, they become hard to manage, right? How easy it is to monitor these services, and again, you need to monitor both the services themselves, whether it's Spring Boot service or Go service or whatever you used, whatever language and framework you use to build them. And you also need to monitor systems that they depend on, such as data stores and any other external systems. So to see why this may be the problem in a current implementation, let's look at what this implementation is actually backed by. So this is Kubernetes cluster that I'm running in the cloud that has these services deployed. And you can see that there are a couple things there. Like if you look at the pods, you will notice that for each service, they're effectively, well, not for each one, but for most of them, for each one that has data store, there is basically one pod for the service itself, and then one service for the database, for the data store, right? And you can see the same thing is the case with catalog store and with order store, et cetera, et cetera. And if you look at what these things are represented in Kubernetes as, those are all deployments. And if you've done anything with Kubernetes and use Kubernetes to manage any stateful workload, you probably know the deployment is usually not your best option because it doesn't provide certain set of guarantees when attaching PVCs and et cetera, that you need for stateful systems, that you need for data stores. What you need to use when you're doing stateful workloads in Kubernetes is what Kubernetes calls stateful sets, right? So obviously this is just a toy demo application, so you can get by with this, right? Because you can show how each of these, their goal was not to show production quality application, but to show how you would go about building services with different languages, making them work together, et cetera, et cetera. So there is nothing wrong, but it's also not the full production environment. So how can we improve that? Right. So the problem with this is there is actually a lot of hidden complexity here, right? I mean, you need to be able to, there are a lot of moving parts. There is data store, there is the service itself. You need to provision and manage both of those. And obviously, the reason they punted on actually managing and doing data stores properly is because data stores are in general hard to do. I mean, if you want to do Mongo, you have to figure out how to deploy Mongo in the cloud. I mean, yeah, maybe you can use hosted Mongo service. I think they call it Atlas or whatnot. But you need to be able to, if you're going to be running it yourself, you need to figure out how you're going to deploy it and how you're going to be managing it. And then the other problem is, we're really kind of pretending that our stateful system is stateless, right? So And that there are a couple issues with that, right? We're trying to say, okay, we have these stateless application containers that we can easily scale. So I can have my shopping cart service and I can scale it to 1,000 nodes, right? I can have 1,000 processes handling shopping carts for millions of customers that are shopping on my website. But if your database that shopping cart service is using cannot scale to support that type of load, I mean, you may, it doesn't really matter that you can scale your stateless processes, right? You need to be able to scale both. You need to be able to scale both your state management layer and your request processing layer, right? And then the other issue is, which I mentioned earlier, is if your data store is down, is your service still up? I mean, it usually isn't. I mean, if you lose your data store, your service basically becomes unavailable. So what we did to change the situation, to make things both simpler and more reliable, we refactored this microservices demo application to be all Java. I mean, except for the front end. We basically kept the front end exactly as it was, and we just rewrote backend services. So we rewrote them all in Java, and in this case, we used Helidon and Coherence. Helidon to implement services, and Coherence to manage data. So you can see that all the data stores, all the external data stores are gone. We are using Coherence as a data management layer, and we are using Helidon as the application framework. So before we go further and look at the application, just a couple of words on Coherence. Back in 2005, I believe, Geir Magnusson jokingly said Coherence is the world's most expensive enterprise hash map. And it was funny because at the time it was actually true. Coherence was commercial-only product. It was fairly expensive, and only select companies were able to afford it and use it to build systems. It was also really just a hash map back then because it was storing data in memory, and it didn't have persistence, didn't have some of the features that it has now that allow you to use it as a data store. And that's changed, fortunately. Both of those things have changed. We've added persistence back in 2015 as part of 12.1 release. And we actually, last year, we open sourced Coherence back in June. So now you have Coherence Community Edition. And everything that I'm going to be showing here, all the demos, everything that I'm doing, actually uses Coherence CE. We don't use any of the commercial features. Everything that you will see today is available to you right now as open source product. So what is Coherence? I mean, if you're not familiar with it, it's the world's first in-memory data grid, which created space back in 2000, 2001. And it actually, even though it's a 20-year-old product, it's incredibly well suited for modern cloud applications because some of the things that we want, some of the characteristics that we want to have in the cloud, elasticity and fault tolerance and the ability to keep going even in the case of failures. Coherence actually had those characteristics from the very beginning, right? It is also a Java library, not really a server. You can use it as a server, but that's kind of, just one option. In the examples I'm going to be showing today, we're actually using Coherence as a Java library, which is embedded into our Helidon application. It's easy to deploy and scale in Kubernetes using Coherence Operator, which we'll be showing today as well. And it's easy to monitor because we have built-in integration with Prometheus, Grafana, and Jaeger. So if some of you may be familiar with Coherence, and if you are, you probably know that Coherence is a distributed cache. But I just want to explain that it's actually, it is a cache, but it's actually a lot more than that. It is scalable, fast, persistent, general purpose KV data store. I mean, you can use it for pretty much anything that you can use Mongo for example, right? It's not lossy data structure. It's something that can be persisted to disk, and you can use it as a system of record. We do store data in memory for fast access. That's how Coherence has always worked, but now we optionally have the ability to persist data to disk for durability. We partition data across cluster members, so you can actually, increase both capacity and throughput of the cluster by scaling the cluster out. By making a cluster bigger, you can basically support larger data sets and higher workloads, higher throughput. We do a number of things to make sure data is as safe as possible. So, for example, we create backups of the data. Like when you put something in Coherence, when you create entry in Coherence, we will create by default a single backup of that piece of data somewhere else in the cluster. And that somewhere else, actually, in the case of Coherence, is as far away as possible from the original piece of data. So what I mean by that is if we have multiple physical machines, we will back up to different physical machines. If we know more about network topology, we will back up to a different rack or to a different data center, different site. So you can have different levels of safety. So at the highest level, in a site-safe mode, you can effectively lose a whole site without losing any of the data, because backups are always going to be in a different site from the primaries, which plays particularly well, again, in a cloud environment with availability domains and availability zones, depending on which cloud you use. So you can use the whole availability zone in a cluster that stretches across multiple zones without losing any of the data. And then functionally, Coherence is not just get and put store. You can obviously do key-based operations such as gets and puts, but you can also do parallel queries. So you can query Coherence to get a subset of the data set that's stored in it. You can do aggregations, things like sum, count, or even write your own aggregations that will do effectively MapReduce processing across the cluster. And we also have something we call in-place processing, which is basically a way to send functions, send some piece of work into the cluster and operate on the data locally instead of moving data across the wire, changing it, and then putting it back into the cluster. It is also an event streaming platform. So we've had support for both server-side and client-side events for a long time, which make it really easy to integrate both. Client-side events will typically be used for things such as updating UI when the data in the cluster changes, and then server-side events can be used as integration points for external systems. So when something is inserted, updated, deleted in the data grid, you can actually you can observe that event and react to it. So you can send a message to Kafka or to JMS or make a call to an external service or anything you like, really. So it's really great integration platform. And in a recent release, we also added support for pub/sub messaging, so you can actually use Coherence name topic to publish messages to, and you can have one or more subscribers that are consuming messages from a topic. So if you need some basic messaging functionality, that's actually part of the product now as well. And as I said, it is still a caching solution, so you can do partitioned or replicated caches. You can do timer size limit on the caches. We also support a number of advanced caching topologies, such as read-through, write-through, which allow you to integrate with the data stores. So, for example, if on a cache miss, we can read value from the database automatically, and when you put something in a cache, we can actually write it to the database, and then right behind and refresh ahead, kind of asynchronous variants of those. So you can use Coherence as a buffer. For example, right behind is typical use cases. You want to be able to do a lot of changes really quickly, and then you want to periodically just write them back to the system of record that's sitting behind the cluster. So all of those things are still supported. Then we also have support for client-side caching with event-based invalidations. We have two features that allow you. First one is called near caching, which allows you to store a subset of the data that was already retrieved from the cluster within the client itself. We call it near caching. So, if the data in the cluster changes, then the client will receive the event and evict the locally cached copy of the data automatically. So on the next request, you will go back to the cache and fetch it and store it in the client again. And then the other option is actually it doesn't use eviction, but it actually updates data automatically. So you could create materialized view effectively of a subset of data that's stored inside of the cluster and could be partitioned across 100 nodes in a cluster. But you can say that, I want to bring this particular subset based on a query. I want to bring this subset into my client and have it cached locally. And if anything changes in the cluster that would impact this view, I want view to be kept up to date. So Coherence supports that as well, which is a very, very useful feature, especially when working with UIs and being able to refresh those UIs in real time as the data in the cluster changes is very helpful. So that's pretty much all I'm going to say about Coherence. I'll give you some resources, links to some resources later if you want to learn more. The other part of the puzzle here is Helidon. In this case, we are using Helidon 2.20, one of the 2.0 versions. And Helidon is basically an implementation of the Eclipse MicroProfile. We're using Helidon MP variant, which is an implementation of Eclipse MicroProfile specification. Right, so it has support for a number of things such as config and metrics and open API support. It also MicroProfile kind of subsumes number of Java EE specs, Jakarta EE specs, such as CDI and JSON binding, JSON processing, gRPC for REST APIs, et cetera, et cetera. So Helidon allows us to build applications that use lightweight Java SE, not Java or Jakarta EE applications, but still applications that use all of these technologies that many of us are already familiar with. It also adds optional support for MicroProfile GraphQL. And then there are some features in Helidon that are kind of specific to it, such as support for gRPC server and client, which is, as Greg mentioned earlier, something that I worked on last year or the year before. I don't even remember. Things are changing so fast. But it's basically what gRPC is for REST services. That's what Helidon gRPC support is for gRPC services. You can do gRPC without protocol buffers. You can do gRPC using JSON or some other serialization format as a marshaller. You don't need proto files, et cetera, et cetera. And it's effectively driven by the set of annotations that you can put on both your service implementation, and then on the client side, you can define an interface that you want your client to implement, point it to the right service on the server side, and Helidon will generate proxy automatically for the client. It's kind of very similar to how MicroProfile REST client works. You define an interface, you put some annotations on it, and that gives us enough information to wire everything together at runtime. So the way Helidon and Coherence are integrated in this particular example, we use CDI to bootstrap Helidon inside of Coherence, to bootstrap Coherence inside of Helidon applications. So Helidon controls the main method. Helidon starts, it initializes CDI, and then CDI extension within Coherence will initialize Coherence and allow you to inject Coherence resources into your Helidon services. You can also inject CDI managed objects into Coherence, and then one feature that's actually very cool when you start using it is you can use CDI observers to handle both server-side and client-side Coherence events. Another integration point is metrics. Helidon supports MicroProfile metrics, which can be directly integrated. It exports metrics in the format that can be directly consumed by Prometheus, and that's kind of the feature that we leverage. So what Coherence does, if it's running inside of Helidon application, it will actually automatically publish a ton of Coherence metrics that will be automatically exported, scraped by Prometheus, and exposed to our Grafana dashboards. The next integration point is configuration. You can actually use MicroProfile config from Helidon to configure Coherence itself, and we use it for a number of reasons, because it makes it really easy to provide default configuration using config files that are packaged as part of the application, and then we can override those settings. For example, when we are deploying to Kubernetes, we can override them by specifying environment variables values for the same config properties using environment variables in Kubernetes YAML. And finally, Helidon has support for open tracing, and Coherence has it as well. So that kind of just works. Helidon will typically create a trace when the request comes in to the gRPC endpoint, but then that request will, as that request goes through the whole stack and goes into Coherence, we can we'll add spans to it that describe which operation is happening and where it's happening, because with Coherence, like if you're doing query, you will do query across multiple nodes. So you will see that query is actually executed in a single trace. You can see that query is executed across multiple cluster members in parallel, and that the results are coming back in, and how long it takes for each one, et cetera, et cetera. So there is actually a lot of cool information you can see and better understand how the application works. We'll look at all of that in a minute. Now, while I personally like Helidon and MicroProfile a lot, and all of the technologies that they support, we also understand that those are not, that's not the only game in town. Obviously, there are other popular frameworks out there. So we just recently released Milestone 1 integration with Micronaut, which has support for a number of things. So you can do dependency injection, you can do event listeners, kind of similar way to what we do with CDI. But then we also have support for Micronaut specific things. So you can use Micronaut data repositories to actually access Coherence. You can use Micronaut caching annotations to store, to do basically response caching in Coherence. You can do messaging, distributed config support. You can use Coherence as a distributed config store effectively. And then we also have support for HTTP sessions for those that need it. And you can find all this in the source code is actually part of Micronaut project. So it's under github.com, Micronaut projects, Micronaut Coherence. And there is actually quite a bit of documentation that explains how to use every feature that's on this list. We're also working on a much better Spring integration. So, we're about to release, hopefully by the end of the month, we will release Milestone 1 for our new Spring integration. And the reason it's 3.0, it's really first proper version of Spring integration, but we've had some attempts at Spring integration before. So version 1 and 2 are kind of already have been used. But Coherence Spring 3.0 M1 should be out soon, and it has support again for similar set of features. You can do dependency injection of Coherence objects into any Spring managed bean. You can use Spring event support for Coherence events. Spring data is supported or is going to be supported. Spring caching, Spring cloud config, and HTTP sessions as well. And we'll probably be adding more features as we go, probably after the final 3.0 release, maybe for 4.0 or one of the later versions. We also have a plan to add support for Spring integration and a number of other things. So just so you're aware, we want to make sure that whichever framework you use, we can support you, and you can use Coherence as easy as possible. So with that out of the way, let's look at the demo. So we have the same application, and the only difference that you'll notice is the change in the URL. So this was in the original SockShop demo, and that used application with the separate data stores that you saw earlier. So now we're going to log into Coherence version of the application and kind of do the same thing just to show you. I mean, it's exact same UI. As I said earlier, we haven't changed front end. We're actually using the same Docker container, Docker image in our Coherence implementation that we used in the original implementation, right? But we can browse the catalog, we can add items to cart, we can check out. So functionally, you can see it all works pretty much the same way, and you can look at it, and you can obviously add multiple things to cart, although there is a bug in the front end that will cause shipping to be charged twice when we do this. So not much we can do there, but oops. That's one of them. Oh yeah, because it's separate things now. So in any case, so you can place orders. Everything is there. You can search the catalog the same way. You can do everything that you were able to do in the original application. But what is different? So if we go back to this, let's see how this looks like in Kubernetes. So here we had separate pod for the service, separate pod for the data store. Here you will see that I basically listed this uses Coherence operator installs custom resources in Kubernetes. So one of the, actually it installs one custom resource, which is Coherence deployment. So you can list your Coherence deployment. And in this case, you can see that we have 6 Coherence deployment, one for cards, catalog, orders, payment, shipping, users. They all belong to the same sock shop cluster, but they have different Coherence role. Role is something that's Coherence specific, and it's basically a way to differentiate different types of members inside of the cluster. And in this case, right now, we have a single replica is configured for each of the services, right? And if we look at the pods, the network's a bit slow. All right, so if we look at the pods, you will see that there is a minor difference here. You'll see that we don't have these UUIDs after a service name, and we don't have actually 2 pods per service anymore. That's I guess the most important part. So we have card 0, catalog 0. We have single pod for each service, and each of these pods, as I explained earlier, each of them has both the Helidon application that's actually serving REST requests for a particular service and Coherence cluster member inside of it. So they're all forming the same cluster. But each one has different set of services. Obviously, cards will have services related to shopping cart management, catalog related to product catalog management, et cetera, et cetera. So, and then what we also have, we don't have deployments anymore. These Coherence deployments are actually backed by stateful sets. So if we look at stateful sets in Kubernetes, you will see that we have one stateful set for each service, right? So that's the setup, right? So each of these pods is both storing data, and right now I don't have persistence enabled. You know, it's easier for the demo scaling out and whatnot. If I want to scale to a large cluster, it's easier not to have to provision hundreds of PVCs every time. So I have persistence disabled, but I can show you later if we have time how easy it is to actually enable persistence and automatically attach PVCs to each of these pods as they're created. So going to management piece. Oops. Where did my... Oh, I've lost. Oh no, it's here. Okay. So I said earlier, it's we have built-in integration with Prometheus, Grafana, Jaeger, and whatnot. So let's look at some of those. Let's look at some of those monitoring capabilities. So this is our main dashboard, and you can see here that right now we have 6 cluster members, one for each service. They're using, I think they're configured with 2 gigabytes of heap each. The total cluster heap is 12 gigabytes and a change. But you will also see that we have 6 endangered services here. And what that means is, because we obviously have single pod for each service, that means that we have nowhere to backup data, right? So card service needs at least 2 nodes in order to backup data. So if you look at services summary dashboard, you will see that card service has a single member, catalog service has a single member, and they're all marked as endangered. You can also see we have a config service, which is kind of shared by all 6. So you can see that it's on 6 nodes and it's machine safe. So you can also see here the requests that came in. Like when I was playing with the application, we got some requests, and you can see which service the requests are for. So you can see there were 4 requests to a shopping cart, 2 requests to the catalog, then 28 requests for the catalog service, et cetera, et cetera. So you can see over time, kind of a map of where the requests, which service is handling most requests, which service needs to handle most load. So let's fix this, and then actually before we fix it, let's look at another piece of information you can see. So here we have. You can look at a summary of caches. So we can see that we have cache for users, which has 5 users in it at the moment. We have 5 shipments. We have 6 payments, 6 orders that have been processed. And my guess is shipments will get to 6 eventually. It's just delaying Prometheus getting the data there, because these should match unless there was an issue with a shipment. So that's basically, some of the stuff you can see. There are actually a lot more dashboards available, but I'm not going to go. Some of them are not interesting for this example. Some of them, go into more detail, like you can drill down into each of these caches and see some details on consumption. It's usually more interesting if there are some indices as well. We can see that there are 8 objects in the cache. They're using 10.8 kilobytes of memory right now. There have been 6 non-optimized queries, so we probably need some indexes here in this case in order to get rid of these, et cetera, et cetera. But those are, just some of the monitoring features that are basically available out of the box for any application that you build this way. Okay, so I guess what I want to do now is show you how easy it is to scale, for one. And then that should also help us with this, right? Once we have more than one member for each of these services, this should change from endangered to the machine safe, just like the config services. So we go back here, how easy is this to scale, right? Because we only have one thing to scale. It's actually quite easy. So I'll do it in a loop, but basically what's actually important here is this, right? So we want to run kubectl scale with the number of replicas that we want, and we're basically just doing it, to simplify things for the demo. We're going to do it for each of these services, right? So we're going to do it for each of the 6 services. We're going to scale them to the same number of pods. So let's scale to 3. And this will take a few minutes because it takes some time for Kubernetes to spin pods up, start a cluster, for nodes to join the cluster, et cetera, rebalance everything. So we'll let that do what it needs to do. And in the meantime, we can look at some of the other monitoring capabilities. Because as I said earlier, another feature that both Helidon and Coherence support is the open tracing support. So we can look at the traces. In this case, I'm looking for traces for the post endpoint, new order endpoint within the order service. So we can see that we had one here. And this one, if we drill into it, this is the order that we just placed 8 minutes ago. And you can see that we got the HTTP request. This is when the trace was started by Helidon. So Helidon web server accepted post request on orders/orders endpoint. And then after that, it called our gxRS on this URL. It called our gxRS order API new order method, which then in turn did a number of things. It actually called multiple services. It calls shopping cart service, which is, you can see it's colored differently because we're using gxRS client to hit different service and get cart information for the user for a specific order. And then it's also calling user service to get information about the user address, credit card, et cetera, shipping address, et cetera. So, and then finally, you can see that the orders, there are a couple of calls to the user service, and then finally the order itself. And each of these actually calls Coherence under the hood. So for example, getting the information, getting the customer information, this is now, so this happens in the repository, which the gxRS endpoint delegates to. This is our repository implementation, which calls get or create user, which in turn makes the request to Coherence. So this part of the trace is where Coherence actually comes into the picture. And you can see that because we only had single node, you will see that request was made on member 4 and request was actually processed also on member 4, right? So that's because we only have single member for that service. But if we had multiple members, this would actually look slightly different, because right now we are not creating backups, so you can only see where the primary piece of data is processed. You would also see backups if we had more nodes. So that's an example of a trace. If we go back here, you can see that we now have 18 cluster members, right? We scaled each of the 6 services to 3 members. 0 services are endangered now. And if we look at service summary dashboard, you will see that each one is machine safe, because we are basically creating backups for each piece of data, wherever on a different machine from the machine where the primary data is. And if we had it again, if we had it across multiple sites, then you would see site safe, which is even stronger level of fault tolerance. So just to show you what I was telling you earlier, let's place an order now. Let's place an order, add something to shopping cart. And we'll proceed to checkout. And if we go back to Jaeger and find the latest trace, you will see now we have some new nodes. So the request is a bit longer. I mean, this is purely because we have JVMs that haven't been warmed up yet. So over time, this should go significantly down. But what I want to show you is actually the fact that when we look at that last order request, so we have put request. In this case, this is still the same because this is read request, so we are not creating backups. But for orders, we have put request, which was executed on member 11, which was then dispatched and processed, hopefully by different member. Yeah, so it was processed by member 6. And then the backup request was initiated by member 6, where the put was processed, and then backup itself was actually created on member 12, coming from member 6. So as I said earlier, you can see like from the very beginning of the HTTP request that came to Helidon endpoint, you can see all the way to what's happening in the cluster. And if we look at, I think I did run the query against the catalog. So if we look at different service, for example, if we look catalog, let's see. So let's look at that one. So, oh, actually, because this is using limit, it's going to be wrong. Now let's look at. So you can see that in this case, we are actually using aggregation. And because we have now 3 members for this service, we are actually sending this aggregate request and executing it in parallel, as you can see from the starting points here, across 3 different members. And again, this is our original member, so it's much faster here. These 2 members, this is probably the first time they were accessed, so they haven't been warmed up properly yet. I mean, none of them are really warmed up properly. I mean, this cluster is fairly fresh and hasn't been used much. But in any case, you can see what's happening, and it's really nice to be able to have this level of visibility out of the box, to understand what's happening, where the HTTP request came in, and then what happened under the hood. Now, if I had persistence, like this is query operation, this is read operation, so persistence would play no role there. But on the previous one, when we looked at orders, you would actually see, if we had persistence enabled, you would actually see that when we do this last part here, that there is actually a persistence to disk happening in parallel with creation of a backup. So you would see it at the same level as this, and you would see that we're effectively writing this put operation is writing data to disk on this particular member. So yeah, that's kind of the level of detail that you can get. So scaling to 3 nodes is certainly nice. You know, we brought the system from something that wasn't fault tolerant to something that is, but we still don't have, 3 nodes is hardly a high scale, right? So let's scale, let's do the same thing. And we'll do Now this is per service. Hopefully I have enough resources. If I crash, I crash, but let's try something. So I'll scale each of these services to 50 nodes. So that should give me 50 pods per service, 300 pods altogether. It should give me a cluster of 300 members, about 600 gigabytes of data. So let's do that. And we can come back to it a bit later. In the meantime, let's look at how this is better. So we have now basically implemented stateful services. They're as easy to scale as the stateless services, right? We could have scaled our stateless part of the service implementation earlier, but now we can scale both. We have only one thing to scale that scales both the data store and the application API processing tier. Another thing that's kind of worth pointing out is because of this implementation, each service truly owns its data. We don't expose a way for somebody to access data. You know, it's one of the microservices tenets, right? Service should own its data. It should not be accessed by external, but by other services directly, et cetera, right? Which is fine, but how do you enforce it, right? Because if I have a separate database, it's easy for somebody, you know, unless I spend time actually securing the database so nobody can access it, which you should, but again, it's more work. How do I ensure that, you know, other services are not accessing my data store directly? Well, in this case, there is no data store to access. The only way to get to the data is through the service itself, right? The high availability is built into the architecture. As I said earlier, I mean, Coherence was created 20 years ago, but when it was created exactly for high availability. It was created as a scale-out solution from the get-go. We can lose members at any point in time. New members can join the cluster at any point in time. There is no manual reconfiguration. Data will automatically be rebalanced and reassigned to different pods. Backups will automatically be promoted to primaries. New backups will be created, et cetera, et cetera. The failover is completely automatic, and there is really nothing for you to do. And it actually works nicer now with Kubernetes in the picture than it did before, because before we could lose members, but we would not replace them because, you know, you had to have something monitoring cluster on the outside and kind of making sure that you have the number of members that you expect to have in a cluster. So if you lose a machine, you will basically lose some members, but they will not be replaced automatically. With Kubernetes, that part is automatic, because if we tell Kubernetes that we want to have 50 replicas, it's going to make sure that we have 50 replicas. If we lose one, if the node goes down, new pods will be provisioned somewhere else, assuming there is enough capacity in Kubernetes cluster, of course. But if we do have enough capacity, new nodes will automatically be provisioned, and Kubernetes will effectively ensure that Coherence cluster is as big as you want it to be, right? So again, going to one of the things that people talk about a lot, but most applications don't actually work that way, is, you know, we want everything to be a kettle, not a pet, right? We want every piece in the architecture to be replaceable, to be, you know, you can throw it away, you can discard it and replace it with a new one. And that's usually easy to do for stateless parts of the application, but not as easy for stateful ones. In this case, you basically get that both for the stateful and the stateless part. And then, as you saw, support for monitoring is built in, and it's also extensible. You can obviously, you know, Helidon allows you to define your own metrics, export them. You can build additional Grafana dashboards. Coherence also allows you to define custom MBeans if that's what you want to do. Because what we basically do, Coherence has all of the Coherence monitoring information that's used for the dashboards that you just saw. That's all coming from Coherence MBeans, which have been around for many, many years, way more than Prometheus and Grafana and all the technologies you saw in action have been around. But what we basically did when we integrated with Helidon, we enabled export of that information to Helidon, to MicroProfile metrics registries. So now, you know, we will periodically export our MBean data to Helidon metric registry, and then Prometheus will scrape it from the Helidon metric registry, and you have all the data. So you can either add custom mbeans and configure Coherence to export those as well, or you can just use Helidon metrics and export custom Helidon metrics to extend your monitoring solution. And last but not least, I feel that implementation is significantly simpler than when we are dealing with things like JPA and dealing with impedance mismatch and whatnot. So to demonstrate that, I'll actually use a different application because it's much smaller. I mean, SockShop is fairly big with 6 services and whatnot, but on the other hand, services themselves are a little too simple because they don't do much. I mean, each service does very little. So this application, I think, is a better introduction on how you would build something like this with Coherence. So I guess we'll dig into that. Oops. So just to give you an idea, starting from the POM file, this is for all intents and purposes really a Helidon application. So you can see the way you define Helidon applications, you basically extend Helidon MP artifact, make it a parent, and then we're basically just referencing some Helidon dependencies and some Coherence dependencies. So in this case, we want to use Helidon MicroProfile bundle, which gives us everything we need for the web server, for our REST APIs, et cetera. We are actually adding GraphQL server and gRPC server as well, so we can support GraphQL and gRPC facade to the same service. Oh, actually, just a quick word. What we are building is really a very simple task management, like to-do list, right? So something very simple, but still big enough to show how you can add data to Coherence, query data in Coherence, modify it, et cetera, delete it, et cetera. So it kind of provides basic CRUD functionality for a to-do list. So that's the application. And then we have basically 3 front ends. We have REST API, we have GraphQL API, and gRPC API for it. So we also added JSON support for JSONB. We want to use server sent events to send messages, because what's interesting about this application, what you will see in a demo, is whenever any of the clients, whether it's gRPC based client, which is JavaFX client, uses gRPC, and then we have React frontend, which uses REST API, and there is also GraphQL frontend, which allows us to execute GraphQL queries. So whenever any of them modifies data in Coherence, we use events to notify all the other clients of the changes. So they're all kept in sync using client-side events. So for that, for REST API, we obviously use server-sent events to propagate Coherence events to the REST client. And then we also have integration with Jaeger for tracing, and some provisions, deploy some built-in gRPC services, such as reflection service, etc. And then on the Coherence side, we add dependency to a couple of things. So we have, first of all, dependency on Coherence CDI server, which is what enables integration with Helidon and CDI in general. So that will, that has CDI extension that will be used to start Coherence cluster member. It will either form a cluster or join existing cluster depending on configuration and whether the cluster already exists. We also have Coherence gRPC proxy, which will allow our JavaFX client to talk to Coherence over gRPC. And then we have MicroProfile config support, which allows us to configure Coherence using Helidon MicroProfile, and metric support, which I described earlier, which publishes Coherence metrics to Helidon metrics registry. We have a couple more things here. So we have Gendex to index our CDI components for discovery, and it also is used by Coherence to index our portable types. And portable types are serialization mechanisms that I'll show in a minute. And this is a plugin that we provide that allows you that will basically implement serialization code for you. So you could use Java serialization. Actually, let's dig into that. So that's pretty much it on the POM side. So it's just a fairly simple application that has dependencies that you need. We have task class, which is really just a POJO that's used to represent a single to-do list task. It has creation time, completion status, ID, and description. So very, very simple class. And this is when I was saying portable types, right? So we could just do implement serializable here, and that class would work perfectly fine with Coherence, but it wouldn't work well with gRPC because Java serialization can be problematic because you need to have the exact same class on both ends of the pipe in order for Java serialization to work properly. And in this case, we don't. We have one task class on the server. We have different, very similar but different task class on the client. So POF allows us to do this, and JSON would allow us to do that, and protobuf would allow us to do that, right? We would be able to generate different classes that look exactly the same, have the same wire format, and work well. But in this case, we're going to be using POF, portable object format, that Coherence provides, both as a storage format in Coherence because it's significantly faster and more compact than Java serialization, and as a way to marshal this class between gRPC client and the gRPC server, right? So all it takes now that we have that POF Maven plugin configured is you annotate your class, you mark the fields that you want serialized. It's actually kind of opposite of how Java serialization works. With Java serialization, you mark things with transient if you don't want to serialize them. Here, you annotate things with @portable if you do want them serialized, and it's intentional because portable actually, in this case, it's a very simple example, but portable types provide, because Coherence can be used for long-term data storage, right? So you need the ability to machine is shut. To evolve these classes over time. So if this attribute was introduced in version 1, then I would say this was introduced in version 1, and I would mark class version. Oops. I would say that this is version 1. So version is 0 by default, and if you don't have since annotation, then the attribute is assumed to be introduced in version 0. So if you, as you go, because this ensures that clients using different version of the class can still interoperate without losing data in the process, because if you add attribute in a new version of the class and then that serialized stream is read by a client that has older version of the class, it will lose data in the process, because it can then write it back and it's not going to write the attribute it doesn't know about. In this case, the way portable types are designed, they will actually preserve unknown attributes and write them back, even if you're using older version of the class on a client that is doing the writing. So that's basically how the data model looked like. And then we have this to-do list service, which is really just a very generic API implementation that will be used by REST, GraphQL, and gRPC facades. So it's just a CDI bean. We inject this task repository thing in it, and we'll get into a second what task repository is. Oh, actually, let's talk about it. Task repository is basically, if you're familiar with Spring, with Micronaut, with DDD, repository is a common pattern to represent something that stores your data, right? So it manages access to tasks in this case. And this implementation in particular extends Coherence Abstract Repository class, which provides a lot of the functionality that's built in, right? This same class is actually used as the base class for Spring Data and Micronaut data integration. So all the features that you see here, in this case, I'm just using Helidon and CDI and kind of implementing this task repository myself. But you can. This is actually for our Spring and Micronaut integration. This is the base that will be used as well. So any functionality you see here will be available there as well. So all this thing does is basically allows us to inject Coherence named map, which is the actual data structure that we use in Coherence to store data. So we have a map of string IDs to tasks, and then we have some abstract methods that are used by abstract repository implementation to either get the map or get the ID from the entity, in this case task, or get the entity type. So another thing, that the reason this is here and why repository needs to know that, we actually have support, which I didn't show. We actually have support for index creation. So for example, in this case, we are doing queries on completion status quite a bit, right? So we want to get either all completed or all items that are not completed, et cetera, et cetera. So we have the ability to mark that particular accessor as indexed. And what this will do is, when the repository is initialized, it will introspect this entity type, and it will automatically create index in Coherence for any attribute that's marked with index. And then indexed actually has a couple options as well. You can specify comparator. I mean, if the attribute is comparable, you don't need to, right? So it defaults to null, but you can specify it if you want to. So you can specify custom comparator for the field. And then you can also specify whether the index should be ordered or not. Ordered indexes are very useful when you're doing range comparison, things like less than, greater than, between, etc. Right? So that allows us to get things from the index much faster. So going back to the repository, that's really all there is to it. So this is what's required to implement repository. Now, this is something that I added just to show, like in Micronaut or Spring, you would typically have Micronaut or Spring generate these finder methods. In this case, I implemented it by hand. So we want to, we need to be able to get tasks based on completion status. So if the argument passed in is null, then we want to get all the tasks. So we are using Coherence always filter to retrieve all the tasks that we know about that are stored in Coherence. Otherwise, we want to only get tasks where task get completed is equal to whatever this completed flag is. And then we call find all method on the base repository class, passing that filter as a criteria. And then second optional argument is the sort order. So we want to get the tasks sorted by creation time, so we always display them consistently in the UI. So that's basically the repository implementation. And then the service now uses different, either the method we just created, we just looked at, or some of the built-in ones to do different things. So let's see what the service actually does. So we have create task method that creates task based on a description, right? So that will basically just call repository save with a new task. This new task will properly initialize task instance. It will pass it to repository. It will store it in Coherence, optionally persist it to disk if you have persistence configured, and then it will return the task that was passed in as the argument. And that will be returned later by the REST API, so the UI can update itself, right? We have get tasks with a status. Basically, we're calling the method we just looked at, find by completion status, just passing that status. In this case, we want to find task by ID, but repository API by default, you use task find by ID method for that, and it will give you the task if there is one, or it will give you null if there isn't one. In this case, we want to throw an exception if the result is null. So we're basically wrapping it with optional of nullable, and if it's null, then we're throwing not found exception. We do the same for delete task, except now we are using remove by ID. If the task is removed, we want to return the task that was removed, so we're passing optional flag there. I mean, a lot of these things, we could have made this the default, but then that creates additional network traffic. So if you don't need the value that you're removing, either don't pass this argument or pass false. But in this case, we want to return the removed task. So in this case, we're passing through to actually retrieve the removed task from the cluster. Delete completed tasks. Now we are calling remove all and passing it again a filter, a criteria. So we want to pass is true filter where task get completed is true. So that will remove all the tasks that are marked completed. And then the last two methods are actually probably the most interesting. And this is something that I mentioned earlier when I said in-place processing, right? So typical pattern in most application is when you want to modify a piece of data, you read it from the data store, you modify it, and then you write it back, right? That's both inefficient and not very concurrent. You have to use transactions when reading and writing, so somebody else doesn't conflict with that. So it actually introduces quite a bit of overhead. Coherence provides, if you think about, like, let's say we have 100 tasks in a cluster of 10 nodes. Those tasks will be spread out. So each node will have about 10 tasks. Not exactly, some may have 9, some may have 11, but it will be about 10 tasks per cluster. So the data will be well balanced across the cluster. So we don't know where any of the specific tasks is. We can find out, but because Coherence knows where it is. But in general, we don't care. What we want to do is we want to tell Coherence, okay, wherever this particular task is, update the description. And that's exactly what this tasks update method does. So we can say our task repository update task with this ID by calling set description method on it and passing in this description, right? And this method, this update method, will return whatever this set description method actually returns. So in this case, this is implemented using Fluent API. So it will return the task itself. So in this case, we're basically updating description on the server and then returning updated task back to the client, which will be then returned to, via whatever REST, gRPC, GraphQL API will be returned to the actual front-end client. And if we get an exception during the update, for example, typically this exception here would happen because we know description doesn't do anything too complicated, it just sets a field inside of a class. So the only time you will get exception here is actually if the task itself is null, so there is no task with this particular ID anywhere in the cluster, in which case we want to throw a not found exception. And then we do something similar for completion status. I mean, it's actually exactly the same. It's just we're calling different method and passing different argument to it. Now, this is not all you can do. In this case, it's fairly simple. We're basically just calling setters. But if you look at what update API supports, you can pass different things. In this case, we're passing by function, which takes task to operate on. It takes a Boolean to set the field to, and then it returns the task. But we could also do value update. If we just had typical setter that doesn't return anything, returns void, that would be the value updater variant, value updater overload. But then you also have the most powerful one, which is the one that takes a function. So you could literally pass a lambda here, Java lambda, and it you will get task as an argument. You could do whatever you want with it, and then whatever you return from that lambda will be returned as the result of this update call. And that lambda will actually be serialized on the client, shipped to the server, executed on the server, and the result of its execution will be returned to the client. So you actually have full control over what happens here. More often than not, it's easy enough to put whatever methods you need on the entity that you want to operate in, and then you end up with a really clean and really simple client call such as this one, right? But you can certainly pass much more complex piece of code from the client to the server. So that's really the implementation. And then on top of this, we have, as I said, GraphQL, gRPC, REST APIs. And these are all fairly simple. GraphQL is probably the simplest one because at the moment it doesn't support events. They all basically just have this to-do list service we just looked at as a dependency, and they effectively just delegate to it, just wrap it and delegate to it and provide necessary annotation. So this is MicroProfile GraphQL specification, which allows you to mark different methods as either mutations or queries. You provide description that will show up in the GraphQL UI or schema. When you run it, you annotate parameters with @name annotation, etc., right? So that's really GraphQL API. It's very straightforward. The REST API is what you're probably already familiar with. I'll get into events in a second. There is some stuff related to events that makes it slightly more complex. But for the most part, like if we look at task creation, so we have a post request, we're passing these things as JSON. We get description from a JSON object, call create task with a description. Get tasks will call get tasks on the API, etc. So it's very, very straightforward. It's just a thin facade around our API. Now, where it does get interesting is how do the events work? So you basically have this SSC endpoint So if you do get on /events, it produces server sent events, right? And what happens here is we register event sync with the broadcaster that was created here when this CDI bean was initialized after it was constructed. So we register event sync with the broadcaster, and we basically, whenever we register a new event sync, we want to let the client know that it connected to something. So we send this begin event, and this begin event, we send information about a cluster member, Coherence cluster member that the client connected to, just so it makes debugging, it makes troubleshooting easier when you're looking in a browser where you're receiving events from, you can actually see that. And then during the initialization, we also add a listener, and this is an example of how you can do client-side listeners, right? So this will actually create, this is a builder for an event listener that handles insert, update, remove events. And in each of those cases, we'll basically just delegate to the broadcaster, we'll broadcast the method to the client, and we will take the task and wrap it into insert, update, or delete event by calling this helper create event method, which really is just, it uses new event builder, passes the name of the event, serializes task classes JSON, and builds the payload to send back to the client, right? And we have something similar, like if you look at gRPC facade, in this case, this is what I was explaining earlier, right? I mean, we don't have any proto files or anything, right? You can do, we're using Helidon gRPC framework to basically define that this is a gRPC service. This is what we want to call it. So, if you want to do protobuf, you certainly can, and you can even build, implement server-side service this way, and then use protobuf, use client written in any language based on protofile to actually talk to it, but you don't need protobuf on the server. We are specifying that we want to use POF, portable object format, that we looked at earlier, as a way to marshal data between client and the server. And then we have a bunch of methods that are really kind of equivalent to our JAX-RS endpoints in the REST API. So create task is gRPC unary method, which for a given description will create and return a task, right? Then we have server streaming method, which takes Boolean as an argument and returns a stream of tasks. In this case, you probably wouldn't want to do it this way, because this will actually send tasks individually back to the client, but it just wanted to show that you can actually do server streaming. You can also do bidirectional, you can do client streaming, et cetera, right? So all 4 gRPC supported method types are fully supported. You just annotate, and you can simplify things by specifying what you expect to see as a request and what you want to send as a response. And with unary methods in particular, it's really, really trivial. I could also make any or all of this fully async on the server. If I was using async API here that returns completion stage, I could actually return completion stage of task here, and then we would have async gRPC API instead of synchronous API that we have here. And finally, let's look at how we do the events here. So in this case, we are passing stream observer, which is gRPC construct, directly, and we have this as a server streaming method. So it means it's, as long as the connection is open and events happen, this method will be sending some data, sending events to the client, right? So in this case, it's very similar. We just say that on insert, we want to call on next on this stream observer and pass it task inserted object, task updated, task removed. And these objects are really, again, just very simple portable types. I mean, once we have, this is all Java 11. Once we have Java 16, Java 17 support, these can all be just Java records, really, because there is nothing particularly interesting about them. They just have some state and a type. So that's it. So that's really how everything is implemented. Now we also have how does it get deployed? So one thing I didn't show you in a POM is we also have a Docker profile here that uses Jib Maven plugin to create Docker image for this. So again, Helidon is a library and set of libraries and with a bunch of dependencies. Coherence itself is just a library. It's just a jar file, or actually a dozen of them or so, depending on which modules you use. So all of those things can be easily packaged together. And we use GibMaven plugin to basically take all of the dependencies based on this POM file, package them together using Java 11 distroless image as a base, and we create this Docker image that's published to GitHub Container Registry, actually. So once that image is created and published, we can then use it to deploy this. And the way it gets deployed is using Coherence operator. So in this case, we are using this, as I mentioned earlier, we have custom CRD, which is coherenceoracle.com v1 API version. The kind of resource is Coherence, Coherence deployment. You can use Coh for short when you're doing kubectl commands, et cetera, And in this case, we're saying we just want to create to-do deployment. We want to have 3 replicas to start with. This is the image to use. We are specifying some, I mentioned this earlier as well. I mean, we have some default configuration here. Like if you look at MicroProfile, so MicroProfile config properties, we have service name is tasks. We have configuration for Helidon to serve our React frontend from the web directory and the resources. We configure Coherence Serializer to be POF, disable proxies, disable topics because we don't need them, etc. So any of these, I mean, in this particular case, we are not overriding, but then any of these could be overridden here, or new ones can be specified. So in this case, we want to specify tracing host to be Jaeger collector. So we, each JVM publishes tracing information to this particular host, which is already running in Kubernetes. And I'm changing sampler to be constant and to always published. So basically, it's not efficient. It's not what you would do in production, but for demos, it's really nice to have every single operation trace. So I'm configuring Jaeger to do that. And then one of the things that we did in the operator, I mean, you can always specify the application type is Java. By default, if you don't specify anything, we assume you just want to run Coherence default cache server, which is fine if you just want to run Coherence as a server. But if you're embedding Coherence into different application, you can specify application type is Java, and then you specify main class that you want to run, which is how you would do it with Micronaut or with Spring Boot, for example. But then with Helidon, because we know what the main class for Helidon is, we can just specify the application type is Helidon, and we'll automatically start the right main class. And then in this case, I actually do have persistence configured. So when I showed the example earlier, I didn't have persistence enabled because I didn't want to do it for the large cluster. But now, because this is small cluster, I'm going to run it locally here on a couple of my servers in the house. Then basically all I need to do is change persistence mode to active, which means we want to store everything to disk, and configure well, in this case, I'm not configuring anything to use because we don't have any specific. It will just use the default storage class, right? So, and I'm just attaching 1 GB PVC to each of the pods that I provision. And then finally, we expose gRPC at port 1408. We expose HTTP on port 7001, and we enable Prometheus Service Monitor on the HTTP port. So that's really all there is to Coherence deployment. If we look at, so that's for my local small micro Kubernetes cluster. It's slightly different for the cluster that I have in OKE. I mean, most of it is exactly the same. I actually disable persistence. So persistence here would be a little bit different, right? So we're actually specifying storage class name because there are different storage classes supported in OCI. So we want to use OCI block volume class that will get to attach storage to each pod, and the minimum storage for block volume is 50 GB. So that's different here. And then you can also do, like we didn't do it in the local one, but here we are basically saying they want to use heap size of 2 GB and request at least 2 GB of space from Kubernetes. So Kubernetes knows what's being allocated. We don't have any limits. You can specify limits, but yeah, that's about it. There is a lot more that you could define here, but this is kind of decent minimum to get things up and running. So let's see. Oops. How this works first. So I think I have everything running. So yeah. So I can create, and again, as I'm creating tasks, I killed this one. Oh no, it did work. I didn't see it. So as I'm creating tasks here or marking them as completed, you can see that it's happening inside. I can do the same thing here. So effects task. You can see it on the other side. I can query for tasks using my GraphQL API. You can see that they're here. This one is completed. This one is not. You can also use GraphQL API to delete completed tasks, the mutating operation. You can see that both of the clients above were updated. You can actually use GraphQL to create a task, and both of them will be updated, et cetera, et cetera. So that's kind of, it just shows you that those events do work both over gRPC and SSC REST API, and that's kind of how the application works. So going back here, let's see what we have. So this is actually running the moment, running locally in my Mac Mini cluster. So if I have limited resource here, but I can still do get pods. I have 3. I can scale them, but before I do that, let me show you that each of these pods actually has PVC bound to it. That is 1 GB each. If I scale this, I'll do it to 6, and we should see that PVCs are being created and new pods are being started. So same thing as before. Obviously, I can't scale this to 50, 100, 200 nodes because I have very, very limited resources in this particular cluster. But again, it doesn't really matter. I mean, if you have larger cluster, you'll be able to create larger deployments, scale them out to more members. But the principle is the same. You simply call kubectl scale. And then interesting thing is, I mean, when we're scaling up or scaling out, we will start, like if you scale to 200 members, we'll start additional members all at the same time, because we want everything to be rebalanced and we want the cluster to know as quickly as possible how many members will there be in the end. But when we are scaling down, that's a bit dangerous, right? And we don't want to, if you scale from 6 to 3, we don't want to kill 3 members right away. And that's something that stateful sets, Kubernetes and stateful sets would do by default. So Coherence operator actually intercepts those scale in, scale down operations, and it will control them. So it will actually, if you want to scale from 6 to 3, it will scale from 6 to 5. And then once Coherence tells us that tells the operator that everything is rebalanced and everything is safe again, backups have been created for things that were moved around, et cetera, then it will go from 5 to 4 and then finally from 4 to 3. So it's it takes longer, but you don't lose data in the process, which is probably a lot more important. So anyway, that's kind of where we are. And these are starting. It will take a minute or two for them to join the cluster and kind of rebalance everything. So in the meantime, let's see what we have here. So we scaled here earlier. Let's pray everything worked. So right. So I scaled every service to 50 replicas, and you can see that we have 50 replicas. They're ready. If we look at pods, we should see 300 of them, 0 through 49 for each service. It is slow. So yes, you can see users 0 to 49, shipping, etc., etc. So it's all we wanted and nothing more, right? I mean, each of these pods now can handle the requests. It can store the data. If we do operations here that you saw across 3 members earlier. Now they will be across 50 members because that's what each service has. Aggregations will be parallel, queries will be in parallel. If we look at here, this should get updated as well. So yeah, so we have 300 member cluster, 0 endangers. We have 640 gig of space, using very little of it. Services, you see that we have 50 members for each service. They're all machine safe, etc., etc. So that is pretty much all I had to show and to talk about. Both of these examples, you can get SockShop from GitHub. The whole application is there. It's actually, you have documentation on how to get it running in your own environment if you want to play with it, if you want to try it. This one uses Helidon. We will be publishing, we actually have the implementation of Micronaut version already, but it's not publicly released yet. We're hoping to release that within the next month or so. And we still need to do the Spring Boot version of it. So that's going to come probably in a few months, probably in a June, July timeframe. But you can look at this and kind of see how the services are implemented, how they work together, how they're wired together, etc. And we also have a to-do list example that I just walked you through, which actually has all 3 implementations already. I mean, it uses snapshot version of the Spring integration, which hasn't been released yet, but it has Spring Boot, Micronaut, and Helidon example for the server-side application. It also has Node.js version of the server, and it has React frontend, the Oracle frontend, Oracle Jet frontend, and JavaFX client that you saw during the demo. So to learn more, as I promised at the beginning, like best place to start is our community website, coherence.community, which has some introductory information. It has links to both demos, and it has links to pretty much everything else that's on this page. So if you remember one link, that's the one to remember. We have our team blog on Medium. So if you go to medium.com, Oracle Coherence, you can find a number of articles. There is a fairly longish, detailed article on what Coherence is, why it was designed the way it was designed, why you should care about it, why you should try it. So I strongly recommend reading that one if you're not familiar with Coherence at all, because it will give you some good background information. And then there is also a series of articles that goes into a lot more detail on the actual implementation and deployment and everything related to the to-do list demo in particular. So that's a good series to start. And then there are some other things like open tracing and Node.js support and .NET client, et cetera, because it's not, I mean, Coherence is a data store in the end, so we do need to be accessible. I mean, it definitely works best with Java because it is written in Java and it's very easy to embed into Java applications. But you can also access any data that you have in Coherence. You can access from C++, .NET, JavaScript, and we're going to be working. One of the reasons we did gRPC proxy so we can do more clients. So we have Python client, Go client, Swift client in the pipeline. So those are all going to be coming hopefully throughout the year. Coherence itself, as I said, is open sourced and it's on GitHub. So if you go to github.com, Oracle Coherence, you can get the source code. You can actually build the product yourself. You can contribute. We're happy to take community contributions. There are also a number of videos for different Coherence features, both the old ones and the new ones on our YouTube channel. And then if you have any questions, if you want to talk to the team, the best place is our public Slack at oraclecoherence.slack.com. So with that, thank you. And if there are any questions, I'm happy to take them.
Yes, thank you, Alex. I'll do the applause for you, and hopefully you hear it from everyone. So
now we can have pizza, right?
Right. Pizza and beer on Okta. Let's go. So we have one question that this guy actually asked like an hour ago, but I didn't feel it was necessary to ask right away. So he says, you know, he worked with IBM WXS, which I'm not sure what that is, but they had a very important case where the data from DB2 was in sync with WXS. And he wants to know if Coherence can like sync your Oracle DB, you know, on startup and put all your data out there.
It can, but that's not part of the community edition. That's kind of more enterprise use case where you would need at least enterprise edition, because that's a feature called hot cache. It basically uses Oracle Golden Gate, which you need a Golden Gate as well. So it uses Oracle Golden Gate to replicate data from Oracle by reading transaction logs and replicate it and put it into Coherence. And then as the application runs and the data changes in a database, it will actually keep track of what's changed. It's a change data capture, right? I mean, that's what Golden Gate does. So we use Golden Gate to capture changes in a database and push them to Coherence. So that feature is available, but it's only available in a commercial version, not in community version.
Okay. So that was our only question there. We did have a comment from Daniel here. It says, thank you to DJug, BJug, and yourself.
Welcome.
Your efforts are appreciated. And then we had a little raffle here for some folks, and they'll see that in the chat. And then you got a round of applause from Ed here.
Thank you, Ed.
I don't know. I mean, I was. You kind of blew my mind a bit. There was a lot of information in there, and
yeah, there is a lot. And I'm sorry if I went too fast, but you told me I only have 90 minutes, and I kind of, which was probably good and bad. I mean, I did get to show you more than I was originally planning to. Like, I did not want to show the whole to-do demo, but I think to-do demo is a nice walkthrough through implementation. So, you know, you got more than I originally planned to do. But it may be overwhelming. I understand that.
Oh, no, I loved it. Any presentation that has a whole bunch of code and then links to GitHub repos is A+ in my book. So thank you very much for doing that. Steven says great presentation as well. And like I mentioned earlier, this will live on YouTube for as long as we leave it up there. And we have no plans.
As long as YouTube lives. Right?
Yeah, and all your demos work. So that was pretty great, right?
Yep.
Yeah, good stuff. Well, thank you. I will. I'll end the broadcast here, and we'll see everyone next month.
All right. Thank you, guys. Appreciate it.